Okay, so today we are back to eating our veg gerbils, building some skills, learning some new tools to put into our toolbox, and then we'll apply them to some DER problems. So basically, we're going to start by learning about optimization. And optimization is like a widely used term, right? You talk about search engine optimization, SEO, and website design. Businesses like to be like, we optimize your portfolio and stuff like that. And so it has kind of lost some of its meaning. But when we say optimization in this class, we mean mathematical optimization or numerical optimization, which is a very clearly defined thing. And so I'll go through today basically how that is defined, some of the structure of optimization problems. Sorry about that. Give a couple DER examples and talk a little bit about basically transformations between problems and some vocabulary for optimization and stuff. So before we get going, who has like taken a whole semester class on optimization before? So no one. And who has at least like done some optimization in a class? Yeah. So is that, leave your hands up if it was an undergrad class. Okay. So what undergrad class did you guys do like computer optimization in?
The only thing that I did optimization for was like for my final like senior design project.
Senior design. Yeah,
Like
that
we
makes
did,
sense.
but like we just did our own kind of like sort of parametric optimization.
Oh, cool. Like sweep some parameters and see what's the best, stuff like that. Yeah, yeah. No, that qualifies. Okay, cool. And then the grad classes people have done optimization in, like any
I took 539, which is machine learning, and then had some options.
machine learning. Sure. Yeah, I mean the core technology that underlies
It
machine
is
learning is
Yeah,
optimization.
minimization
For sure.
is a cool thing, yeah.
Right, exactly. Yeah, so that's one huge application of optimization that has really exploded in the last, decade-ish. So we'll talk a little bit about that, but it won't be the focus of this class. Cool. Any other grad classes that you've done some optimization in?
There's just robotic class where you want to
Robotics and model predictive control. Yeah, so that'll be much closer to the kind of stuff that we'll talk about here. Okay, so we'll start by talking about optimization problems. Just what are they, and how do we kind of transform mathematical statements into these kind of precise definitions? We'll talk about vocabulary, things like optimality and feasibility and so forth. And then we'll talk about basically tractable versus intractable problems, where tractable roughly means you can solve it well in a reasonable amount of time. Okay, so our goal here, just to kind of set expectations, is not to learn everything that there is about optimization, which would just take way too long. Like you could do multiple, years of graduate study and still not really get all the way there. So we want to be good users of optimization, and specifically a class of optimization called convex optimization, which happens to be very well suited to the kind of DER design and control problems that we want to tackle in this class. So just in general, optimization is an extremely broad and very deep field, both theoretically and methodologically, computationally and things like that. So a wide range of actually physics problems can be recast as optimization problems, chemistry as well. So you can think of the principle of least action in Hamiltonian or Lagrangian mechanics. You can think of the principle of least time that light follows when moving through various media. And there's other things like that. So a lot of problems that are, traditionally were kind of physics or mechanics type problems actually can be reframed as optimization problems, which is a hint that optimization is hard, right? Because there's a lot of hard mechanics problems that you can write as optimization problems. So it's at least as hard as those, and maybe harder, right? So it turns out that most optimization problems are intractable. And I don't mean there that you can't even get any kind of solution to them. What I mean is it's really hard to efficiently get the best solution, right? But to do pretty well maybe is tractable. So there's kind of a notion of tractability that we'll discuss a little bit more. But there's a class of problems called convex optimization problems that are usually tractable. And so for this class of problems, there's a rich and beautiful theory. There are efficient and reliable algorithms for a wide range of these convex optimization problems. There's convenient modeling software. So by that, I mean, essentially, the process that you go from when you have a problem on paper that you want to solve to eventually having something that like you can give to a solver and get back a numerical answer. 27 or whatever. And so that process, depending on the software that you use, can be super annoying or really easy. And so for convex problems, it turns out that that process is actually very easy due to some software that's been developed over the last kind of decade-ish. And then so non-convex problems, of course, is anything that's not a convex problem, and we often encounter those in practice. And it turns out that convex optimization is often used as a subroutine in a non-convex problem. So you can think of this as kind of like solving analogous to solving nonlinear equations, where you use something like Newton's method, where basically you linearize, and then you solve a linear equation, which is easy-ish. And then you kind of move to the solution of the linearized problem. And then you look at the nonlinear problem again, and you relinearize about that new solution, and you kind of iterate like that. And if everything goes well and you're lucky and things like that, you converge to some solution. So there's kind of an analog in optimization where you have a non-convex problem you're trying to solve, you kind of convexify it. You come up with an approximation that is convex, you solve that, and then you go back, at the new solution and sort of convexify there and iterate. So there's value in learning about convex optimization, even if we end up solving non-convex problems. And there's a wide range of applications. Machine learning is a huge one. Control is another, design optimization, and many other things. So we won't go deep in this class, but I do recommend, like, as engineers in the modern world of AI and machine learning sort of ruling everything, I think it just is, to be a well-rounded technical person, I think it's valuable to take a class on optimization, and maybe a class on data, right? Probability, statistics, machine learning, something like that. You'll probably use some of that in your future, either in research or eventually in product development in a company if you go that route. But it's also just, I think, helps you understand the rapidly changing world around you. Right? So anyway, that's just my spiel, my recommendation. But okay, so what is an optimization problem? And there are many ways to formulate optimization problems, but a general one that we'll use here basically takes this form. So we want to choose a variable x, and this is an n-dimensional vector. And you can, of course, formulate optimization problems that don't have vectors as variables. They have just one number, a scalar, or maybe they have a matrix as the decision variable. But we'll study problems that have vector-valued variables. And we want to minimize something, a scalar valued function of that variable x. So f naught maps n-dimensional vectors into one-dimensional scalars. And then we have a number of constraints. We have m of them in general. And they all take this form of kind of an inequality where the right-hand side is equal to 0. So this looks like a very specific form of problem. We have these scalar inequalities. We have a scalar valued objective function and things like that. But it turns out that this is, in fact, very general. Okay, so how do we interpret this? So basically, the problem is to choose the best feasible, and I'll define what feasible means in a sec, n-dimensional vector. And so the variable x, this is the thing, the choice that we're making, or the action that we're going to take. And the objective, this function f naught, quantifies basically how bad x is. So we want to minimize that. We want to come up with like the least bad solution. Alternatively, you can come up with an objective function that you want to maximize that quantifies how good x is, and then you have a maximization problem. And it turns out that you can always reformulate a maximization problem as a minimization problem, and I'll show how to do that. And so what does this term feasible means? Well, it means two things. Basically, it means, first of all, that you can evaluate each of the functions that showed up in the problem statement, f0, the objective function, and all the fi functions and the constraints, that you can evaluate all of those. They're sort of well-defined at x. And so a counterexample of that is if you had a logarithm in one of your objective or constraint functions. And so there, for the natural log is only defined as a function for positive arguments. So log of a negative number, at least if we're dealing with real numbers, not imaginary numbers, is undefined. So first of all, the problem has to be sort of well posed in that sense, right? And then x also has to satisfy all of the constraints. So feasibility doesn't say anything about how good or bad a given value of x is. It just says that it's like acceptable in some sense, that it's not going to violate any constraints, break any laws, things like that. So that just means that fi of x is less than 0 for all I. And I'm going to throw a lot of new stuff at you. So please, if you have questions or comments, just feel free to raise your hand, or if folks are on Zoom, to speak up. Okay, so let's talk about a couple DER examples quickly. So you might have a problem where you want to come up with a good size of a solar photovoltaic array. And so you'd have some numerical decision variable that quantifies the size. So this could be the number of panels, or it might just be the rated power of the array. And you might want to, you might have a range of objectives that you want to balance through different prices or weights. And they might include the initial cost of the hardware, installation labor, permits, all that sort of stuff. They might also include energy costs, or the amount of money that you might save on energy costs by having solar power. They could include something around greenhouse gas emissions as well. And then we might have constraints related to a budget. I only have 15K to spend or something like that. We might have a limited rooftop area. So maybe I only have a certain number of square meters, and maybe it's pointing in certain directions and things like that. So that kind of constrains the design space. And then we have equations, mathematical equations that describe basically the power output as a function of a bunch of other stuff. The available kind of solar resource, the irradiance, on a horizontal surface, or measured with that telescope-looking thing that points directly at the sun, so a normal surface to the sun's ray, and all the geometric stuff that we learned about 2 lectures ago, right? The tilt angle, the orientation angle, the time of day, the season, all that stuff. Okay, so those things can enter as constraints. So another example, a kind of classic example in the DER world, has to do with electric vehicle charging. So suppose here that we have a bunch of EVs. Maybe you are Tesla, and you have a bunch of customers who all have Teslas parked in their garages, and they all want power by certain deadlines when they get up in the morning and drive to work. And they've chosen, I want 85% power by 6 a.m. or 95% power by 8 a.m. or whatever it is. And so you can choose basically when you charge the vehicles in order to shape the profile, the total power profile of that whole kind of aggregation of vehicles. And you don't probably want to do it just at one time. You probably want to do it over a bunch of times, looking forward, maybe over the whole night, something like that. And so again, we might have energy costs as an objective. So the value of electricity might be different at different times. Greenhouse gas emissions, again, can be different at different times. If you have in Texas, for example, oftentimes they have a ton of wind power overnight. And so electricity can be very cheap and very clean. And you might also care about the peak electricity demand, which determines basically how big things like wires and transformers need to be. And you could have constraints related to basically the equations that govern the energy evolution of the battery, right? So we've talked about those a bunch of times. We also have constraints. In last lecture, we talked about kind of a general battery type model that modeled a bunch of DERs. And so you might have a limited amount of energy. You might also have a minimum amount of energy that you won't go below. And then you have limits, again, on the sort of how quickly you charge or discharge the vehicles. And we have deadlines as well that come from maybe apps people enter data into. Okay, so those are just a couple of DER type problems, and we can investigate them in more detail once we know a little bit about these optimization methods. So it helps, basically, there's kind of an informal mathematical field, which is all about kind of modeling gymnastics that you do to transform optimization problems into other, hopefully easier or more informative optimization problems. And so that involves basically interchanging equivalent statements of optimization problems. So 2 problems are equivalent, meaning you can kind of interchange them. If you can get a solution to the first one relatively easily by just solving the other one, the second one, and vice versa. So there's kind of a bijection, 2-way equivalence between the problems. So one example of that is just this interchange between maximization and minimization. So suppose that rather than having a function f naught, which quantifies how bad a candidate solution is, we have this function g that quantifies how good it is. And we want to solve a maximization problem, choose x to maximize that function g, which you can think of as value or revenue or benefit, something like that. And we still have a bunch of constraints. Well, equivalently, we can kind of put that back into the kind of canonical framework that I showed in the early slide there by just minimizing negative g. So here our objective function f naught would just be negative g of x. If you have a constant in the objective term, often comes up. It turns out that minimizing this f naught plus any constant a is equivalent to just minimizing f naught. You can kind of see how that works, right? The decision doesn't really affect that constant term, so you can just strip it out. Now the what's called the objective value, the solution of this, the value x here would be the same regardless of which problem you solved, but the objective evaluated at your best x that you found would be different, right? They'd be different by a value a. So this is kind of a subtlety in the notion of equivalence that we talked about. Basically, what you care about is that you get the same solution, whether you solve either problem, not so much whether the optimal value is the same, if that makes sense. I'll talk more about what those terms mean in just a second. Okay, so yeah, we can also do transformations on the objective function or the constraint functions. So suppose we have some function 8 that is h rather, that is increasing, which means that, you know, if some value y is bigger than z, so y is 10 and z is 3 or whatever, then h of y is always going to be bigger than h of z. So if that function h has that property, and if we have a bunch of functions or if we have a bunch of functions gi, such that gi of y is non-negative whenever y itself is non-negative. Then this problem here, the kind of basic problem that I showed earlier, is equivalent to you know, this other problem here where we choose x to minimize this function h of f naught of x. So oftentimes you might have something like a Gaussian thing in the numerator, or sorry, not the numerator, the objective function. And then you'd use h as maybe the natural log, something like that, an increasing function. And then you might take the log of, you know, a Gaussian or an exponential, which would give you kind of a linear type term. So that problem might be much easier to solve. And then you can transform the constraints as well if you want to. And so you just basically wrap the FIs and the GIs, and then these problems end up being equivalent. Okay, we also had a bunch of stuff less than or equal to 0. Well, that seems kind of restrictive. What if you have it less than or equal to some other function here, right? But it turns out you can write this thing, g of x less than or equal to h of x, this constraint, as just the form that we talked about. You know, f1 of x is less than or equal to 0, and we just make this definition. You know, you subtract h from g, and then that whole thing on the right left-hand side, rather, g minus h has to be non-negative. And then greater than or equal to constraints also work just fine. Basically, now we just subtract g from h, and we've again got a non-positive constraint. This makes sense so far. This is like, today's lecture is a weird mix of like totally obvious and rather subtle. So I'm going to approach it all with the same kind of deadpan. And if you guys get confused, please raise your hand. Yeah, what's up? Yeah, I just meant like a Gaussian, like a bell curve kind of thing, which has an exponential in it. All I was trying to get at there is an exponential function looks kind of weird and it might be difficult to deal with computationally, but if you take the log of an exponential function, you end up with just like sort of a linear thing, which might be much easier to deal with. So that that log transformation is basically allowed. That's all I was trying to say. Does that make sense?
Yeah.
Okay. Okay, I also showed a problem that only had these inequality constraints, a bunch of things less than or equal to 0, but we could also have equality constraints. And the way that we could incorporate those, basically do a transformation and put them into our basic framework, is just to define a couple of inequality constraints. So g is equal to h means that g is less than or equal to h, and g is greater than or equal to h, right? You kind of intersect those things logically, and you get that g must be equal to h. Okay, so now we have two inequality constraints, and then we just do what we did in the previous slide. We subtract stuff over, and then we get basically non-positivity type constraints here. Okay. So sometimes it's helpful to leave problems that have equality constraints, to leave them in that form. It can be algorithmically beneficial, but you know, theoretically, it's general just to think about inequality constraint problems. So that's a useful kind of modeling trick.
So you said sometimes just writing it in an inequality form can help with the computing time. Is that what you're getting?
Actually, the opposite. So the question is just, can you, when you write it from equality constrained into inequality constrained form, does it speed up computation? And actually, sometimes I think it's the opposite. So sometimes if you have a bunch of inequalities and you transform it into equalities, which you can also do, right? Then sometimes that problem, which might be more structured, could be easier to solve. Yeah, exactly. Yeah. So it's like, I'm not really making value judgments on things right now. I'm just
Yeah.
like saying these are a bunch of tools you can use to mess around with like the modeling gymnastics of optimization, more or less. So, and when you use them, it's kind of it's the craft of optimization modeling, right? You have to get a little bit of experience to figure out and try and fail and get it wrong, try again, that stuff. Okay, there's something called feasibility problems. So sometimes we don't really have an objective that we're trying to minimize. We just want to make sure that a bunch of constraints are satisfied. So in that case, we might want to just say, find any x, not necessarily the best x, just give me any one. And all I really care about is that a bunch of these inequality constraints are satisfied. So in an optimization framework, we can solve that, right? By basically minimizing 0 or any constant or whatever you want to do, and subject to all the same constraints. So here, minimize 0 just says like, I'm indifferent, right? I have no real objective here. I just want the feasibility problem solved. So to show kind of how optimization is pretty challenging, if you think about solving a system of nonlinear equations, m nonlinear equations, right, where m could be very large, it could be a billion, say. So solving that problem is super difficult in general for a general nonlinear functions and high dimensional variables. But that's a feasibility problem. So find x subject to, and then we just do our tricks here where we turn these equality constraints into these non-positivity constraints. And now we already showed that a feasibility problem you can reduce to an optimization problem. So in some sense, if we can come up with an optimization solver, then we have solved this other thing, solving nonlinear equations, which is pretty difficult to do efficiently and exactly. Okay, so that's just to convince you again that optimization is like pretty rich and challenging. All right, so let's talk about a little bit of vocabulary having to do with optimization. So we kind of classify problems based on like how solvable or how well posed they are. So we say that a problem is infeasible if there is no feasible x, right? So that means that for all x, one of two conditions is satisfied. Either you can't simultaneously satisfy all the constraints, or some of the functions, the fi functions, are undefined at that value of x, or for all values of x. So as an example, suppose we're trying to minimize x, just make it as small as possible. X is a scalar variable in this example, subject to two constraints where we want x to be bigger than 1, and also we want x squared to be negative. So the only thing really well, nothing, no real number is going to satisfy both of these constraints. So we say this is an infeasible problem. If we're dealing with complex variables, maybe we could think about a different version of this problem, but here we're only talking about real valued variables. And then we call a problem unbounded if basically you can come up with a sequence of x that just get better and better and better forever. And they stay feasible, right? But you can basically make the objective go to minus infinity. So as a simple example of that, suppose, again, we have a scalar valued variable x, real scalar, and we're trying to minimize the log of x, which that's this function here. And so implicitly, they were in this problem, minimize log of x. I didn't say any constraints like subject to stuff. But remember, feasibility means that all the functions, the fi functions, are defined at the value of x there. So this thing really is only defined for positive x. So we want to make x smaller and smaller. And we do that by going closer and closer to 0. So you can imagine the sequence here where you just take the old x and divide it by 2. So you start at 1, and then you go to a half and a quarter and so forth. And as you get closer and closer to 0, your objective value just gets better and better and better. So we would say that this is an unbounded problem. Okay, so then let's talk about optimality. So we'd say that something x star and a star in optimization typically denotes like a solution, right? So an x star in Rn is called optimal or an optimizer. If, again, two conditions, first x star has to be feasible. So all the functions have to be defined at x star, and all the constraints have to be satisfied at x star. And then we also have the subjective thing here, which is that the value, the sort of how bad x star is, can't be any bigger than that same value of x for any other feasible x. And so infeasible problems have no optimizers, right? Nothing is feasible, so obviously this first condition can never be met. And then unbounded problems also have no optimizers, right? Like in the minimize log of x example, there is no numerical value of x that's better than all other values, right? Because you can always take x over 2 and it would be even better. But if a problem is feasible and it's bounded, you'd think, okay, then we have a solution, right? And that's true, but you can also have multiple solutions. So it may not just be one x, it may be a couple of x, or it may be an infinite number of x, actually. So for an example of that, suppose we have a two-dimensional variable, x1 and x2, and we're trying to minimize that second coordinate, x2, subject to this constraint x2 is equal to 1. It's a totally weird thing to do. It's not a problem that would come up in reality, but problems like this do come up in reality. So this one illustrates them. So here's the plane, x1, x2, and we want to make x2 as small as possible. So we want to kind of move downward in that direction. But we're stuck on this line here, which is the line in R2 that satisfies x2 equal to 1. That's basically the line y equals 1. So any value, any point of the form x1 comma 1, any point here is optimal. So there's an infinite number, a continuum of those points. Okay, so let's talk about local optimality as opposed to optimality. So with no qualifier, optimality means kind of global optimality. So we're not local or optimal just in a neighborhood, but we're optimal over the entire feasible set or feasible region, the set of all things that satisfy the constraints. So x tilde is locally optimal, or we say it's a local optimizer if it's feasible. And we have this objective thing again. So we're better than any x, but only in a neighborhood of x tilde. So here, neighborhood is like this mathematical term, right? There are precise ways to say it, but it basically says, if you can draw a little blob around this x tilde and say within that blob, x tilde is better than any other option, then this x tilde is locally optimal. But you can get unlucky with a local optimizer, right? So it may in fact be much worse in terms of the objective value than a global optimizer. So here I'm showing some objective function that's kind of wiggly. This is our f naught of x. X is the decision variable here, just one-dimensional. And this is the global optimum. In this case, it looks like it's probably unique, although it wouldn't have to be. There could be a flat part here, where then you would have basically a little line segment with an infinite number of optimal solutions on it. But here it looks like a unique global optimum. And so you can imagine if you did a kind of simple algorithm that started over here and just said, well, go in the direction of decrease of the function. That's an algorithm called gradient descent, and we'll talk about it in a couple of lectures. So if you did that, you just kind of keep moving downward, you'd eventually get to this point, and then you'd say, oh, the gradient is equal to 0. And we know from calculus that gradient equal to 0 means local stationary point, right? Local minimum or maximum, or saddle, I guess. And so then you'd stop. You'd say, I won. I found a local minimum. And I don't know, maybe this is a billion on the y-axis, and this is negative a billion or something. So you could have an arbitrarily large difference basically between the quality of your local solution and the global solution. But sometimes local optima actually do really well. Sometimes they're really, really close. Sometimes they all actually are the or a global optimum. Okay, so with some vocabulary and a little bit of background under our belt, let's talk about tractability of optimization problems. Because again, we're trying to sort of find a class of problems that are basically solvable in a reasonable amount of time. Yeah, so in calculus, like probably a vector calc class, maybe calc 3 or the end of calc 2 or something, you probably learned some techniques for optimization that had to do with maybe something like taking derivatives or gradients and setting them equal to 0, and you get a system of equations out of that. You solve that system, and then you do a bunch of testing. You say test to make sure that it's feasible with respect to all these constraints and stuff like that. And that process can work, and sometimes that's a useful tool to have in your toolbox. But the set of problems that can be solved with that sort of analytical, pen and paper approach is really small compared to the set of all the things we'd like to solve. Right. So, but the set of things we can solve numerically is actually much bigger. So, so we're talking about numerical optimization in this class. So in general, with these numerical optimization problems, to solve them globally requires an amount of time or a number of computer cycles, something like that, processor cycles, that is exponential in the dimensions of the problem. So here n is the dimension of the decision variable x, and m is the number of constraints. So so something that grows exponentially is bad. But usually to solve something locally, you can use a kind of simple algorithm that's pretty fast to run. And typically that algorithm runtime will only be exponential, or sorry, only polynomial in the dimensions of the problem. So here I'm showing basically the difference between some exponential functions and some polynomial functions. So this is a semi-log plot where there's a log scale on the y-axis. And this is just the value of a bunch of different functions. And then on the x-axis, this is a linear scale. So we're just going from basically dimension 0 up to dimension 100, which 100 variables is not very big. Okay, so all of these functions here, the polynomial functions, n cubed, n to the fifth, they all look kind of flat, right? Which just means they're growing quite slowly. And then the function 2 to the n, this is kind of the simplest exponential function you can write down, looks like it's growing much more quickly. And so here, we're at 10 to the 30, whereas we're at so this is, I don't know, whatever number of charged particles in the universe or something like that. And then down here, we are at about 10 or 100, somewhere in that range, maybe 1,000. And then if we take n to the n, so this is another, way worse exponential growth thing, we get this just absolutely astronomical increase. So if you're writing an algorithm and you're like, how long is this going to take to run on my laptop? And that time scales like n squared or n cubed, that's like not too bad. But if it scales like 2 to the n, that's potentially a nightmare. You might be in a situation where you have to run your code in a cluster and let it go for a week and stuff like that before you converge to anything meaningful. Okay, so I want to give you an example of a totally benign looking problem that ends up being, in fact, intractable by this, by the metric that the worst case complexity, the worst case time that it takes to solve a problem grows exponentially in the dimensions. So this is called the knapsack problem. Knapsack is like an old word for backpack. I guess people in the 50s, computer scientists, I don't know, said knapsack rather than backpack. But anyway, so the idea here is we want to choose some n-dimensional variable, and we want to maximize a linear function of that variable. So you can think of the elements of this matrix or vector C here as being basically the value of something. And then we have a bunch of constraints that basically say, one constraint that basically says a linear combination of these things has to be less than or equal to something, some number b. So you can think of this as like I'm a cat burglar, and I have climbed up on the outside of some fancy person's house and pried a window open and gone inside, and I found the box of jewelry or whatever. We call that jewelry box. I don't know, some word for it. Anyway, and I've got a backpack, right? And I want to fill up basically as much as I can put into the backpack and maximize the total value. So here the C things would be like what I think I can pawn all the jewels and gems for. And then the B here is basically the size of the backpack or the weight that I can carry, maybe. And then the AI terms that would show up in here basically would be something like the weight or the volume of the goodies that I'm stealing. So I'm trying to cram this backpack full of juicy stuff. But these things, we have one more constraint. So this thing here, so far, this is a totally benign problem. And we just add this really simple looking constraint that says that each of the xi's, they have to be either 0 or 1. So all I'm doing is I'm making a binary choice with each gem or jewel or necklace or whatever that I pick up and saying, should I put it in or not, right? Okay, so that's the knapsack problem. So this thing, it turns out, is what's called NP hard, actually NP complete. So who's heard of the distinction between P and NP before? Okay, so P is basically the set. This is a classic computer science dilemma. It's an open question, maybe the most important open question in computer science is P equal to NP or not? So P is the set of problems whose solution time basically can be upper bounded, even in the worst case scenario, by a polynomial in the size, the dimensions of the inputs. So here, like a polynomial in n. And then NP is the set of things that, if I give you something and I say, hey, this is a candidate solution to the problem, that you can check all the constraints and stuff. you can check all those and see that it's feasible in polynomial time. But it's not known whether you can come up with an algorithm to actually generate a solution in polynomial time. Okay, so if you solve this problem, which is an NP complete problem, then you have proven that P is equal to NP. In other words, that it's sort of as easy to solve one of these NP problems as it is to solve a problem in P. And there's $1 million prize for that. So if you want some quick money, just come up with a polynomial time algorithm for the knapsack problem, and you're good, right? You're set for life. There's a link here even. This is a link. So if you want to make $1 million, thank me later. I'll take a small finder's fee. Anyway, the point here is that this is just a totally like banal, just super benign looking problem, right? It looks very simple. It's got these like, just 0 or 1 choices and one constraint, a simple linear objective, but it ends up being super hard actually to solve. And by solve here, I mean to solve exactly and globally, guaranteed even in the worst case in polynomial time. That doesn't mean that you can't come up with a good solution or even the best solution for most problem instances, maybe not pathological ones. It doesn't mean that you can't solve this problem kind of pretty well in terms of engineering practice, right? But anyway. Okay, so that's sort of the notion of tractability that we're dealing with here, is this sort of global solution in polynomial time. Okay, so just to contrast local and global optimization. So a local optimizer at x tilde, again, we talked about this, it's kind of optimal in a neighborhood, but not necessarily everywhere. That a local x tilde, we can usually compute pretty efficiently using fairly simple algorithms, but it might be far worse than a globally optimal solution x star. You kind of don't know. There's sort of no guarantees. It might be really good, but who knows? And then by contrast, a global optimizer typically, is pretty slow to compute, or might be. And in this kind of, bad problem, like a knapsack problem or other NP hard problems, which there are many of those, it might take super long. If you have a big problem, it might take, years or more to solve exactly. But you're guaranteed, if you find a true optimum x star, you're guaranteed that you have the best performance among all the kind of acceptable options. So there's this kind of trade-off. And then it turns out that for convex problems, that trade-off goes away. That all of the local solutions end up being global solutions. And so you can run these, fairly simple, fairly efficient algorithm, do it sort of naively, end up with something, and you just know you have a certificate because your problem is convex. It's the best you can possibly do. So you can imagine how that has both computational and also sometimes maybe theoretical advantages. So anyway, there's this notion of convexity, and it ends up being really important, and we'll talk more about it in the next couple of lectures. So I want to just give a couple of examples of convex problems that get solved very often, in engineering practice, and that we'll solve fairly often in this class. So probably the classic one is called the least squares problem. And it basically generalizes, the problem of minimize x squared, where x has to be in some interval. That's a scalar value problem, right? It's quite easy. You have a quadratic. You can take the derivative. It's all smooth. Set it equal to 0. You get a linear equation out of that gradient equals 0 thing, and then you can just solve that by hand really quickly. So, so that's where when a dimension n is 1, but when x is a higher dimensional thing, it turns out that that's much more difficult to do analytically, but we can do it. And that's why this problem really is famous, is because it has a clean analytical solution that's easy to compute. So the problem here is that we want to minimize something like x squared, right? So we have a linear function of x, ax minus b. We take the transpose of that and multiply it by itself. So that, y transpose y is basically the vector version of y squared. Okay. And then we have input data, which is our matrix A or vector B. And we assume that B is in Rm, where m is at least as big as the dimension of the vector. So here, basically the matrix A is tall, which means we have essentially an overdetermined system of linear equations. And so we can't come up with any variable that's going to exactly solve all of those linear equations. So we're kind of looking for the one that's closest to solving all the equations in this kind of least squares sense. So the idea here, sorry, I just said all this out loud. Yeah, so we have basically no x is going to solve all the equations, but we want to find an x that's basically close to solving all the equations. So this thing has an analytical solution, which is super famous. This thing here, A transpose A inverse times A transpose. This thing is called the pseudo-inverse, or the Moore-Penrose pseudo-inverse of the matrix A. So you just compute that pseudo inverse thing, and then you multiply it by the matrix B. And in MATLAB, there's a command that does this. It's just A\B. And this backslash command actually does a whole bunch of other stuff, but it's kind of the go-to thing in MATLAB for solving a system of linear equations. Not necessarily when A is tall, but kind of in any value of A. And to solve least squares, basically you're inverting a matrix, more or less. And so the solve time kind of in the worst case scenario goes like n squared times n. So this is a polynomial in the dimensions of the problem. So that means there's a polynomial time algorithm for least squares. So I'm going to show briefly where that comes from. So if we have a quadratic function here, x transpose times some square matrix P times x, plus a linear function of x, some vector q times x, plus some scalar r, where P is symmetric. So that's what this means, P equals P transpose. We take all the rows of A and write them as columns. That's the transpose. And basically it means that this thing is symmetric. So then if we take the gradient of this function, it has a simple form, and you can kind of convince yourself of this. It's just 2 times P times x plus q. So if you think of this as a dimension 1, right? So x is a scalar. Then here we just have P times x squared, where P would be a scalar, plus q times x plus r. And so if you just took the derivative, the scalar derivative of that thing, you'd get 2px plus q. So that's all that's showing up down here, but basically in this kind of nice matrix form. Okay, and then we can apply this rule for taking the derivative of a quadratic function. We can apply that to the least squares problem, where our matrix P is just A transpose A, and that thing is symmetric. If you take the transpose of it, you can see that it's equal to itself. And our Q value here is -2 A transpose B. So we can see that by basically expanding out, doing FOIL. First, outside, inside, last. Do you guys learn FOIL still? Okay, cool. So basically we FOIL this thing, but using matrices and vectors rather than scalars. So first of all, we can distribute the transpose on the left-hand term here. So this thing becomes x transpose A transpose. So if you take the transpose of a product AB, basically you switch the order and then you transpose each of the things inside. So here I'm switching order and transposing, and then minus B transpose. And then I haven't done anything on the left-hand term there. And then we just kind of factor this thing here. So we've got x transpose A transpose times AX, that's our first term. And then we have the outside, inside, and last terms as well. And then it turns out that these two terms here are equal. And you can see that, again, by applying the rule of transposing products. So you switch the order. So you go B, A, X, if we transpose this whole thing here. And then the transpose of the transpose is the original thing. So we get back to here. So we can write that as 2B transpose A plus B transpose B. So, so now we can identify this function, this kind of general quadratic function here with our least squares function here. And then we get the derivative of the least squares cost function, objective function. Okay, so then we write down the gradient, which is just 2 times our P matrix, which is A transpose A, and then plus B, which in our case is, plus Q, which in our place is 2B transpose A with a negative sign. So we take all of that, that's the gradient of F, and we set it equal to 0 and we solve. And then you can see you move this thing to the right-hand side, the 2's cancel, and then we take A transpose A and we invert it and multiply it over here by the A transpose B. And so this is our least squares solution. And it works as long as this thing A transpose A is invertible, right? If the inverse exists. And it turns out that that holds if the rank of A is equal to n. So A is full rank. So who remembers all that stuff, like rank and invertibility and so forth from linear algebra? Who's like, that's easy, I got it. Okay. Not so like half the class. Something. Okay, so why do we care about this least squares problem? Well, it turns out it shows up just all over the place in all sorts of applied math. One example is in the machine learning world, in the model fitting world. So here, the interpretation of that B vector is we assume that each B basically is a target that we want to predict. So you could think of this as being like the electricity demand of a community that we're trying to work with, as a DER coordinator, something like that. And then all the terms AI, J, these are observations, I, of n features that we have. And so features are basically just information that carries some, or data that carries some predictive power over the thing, the target that you're trying to hit. So for predicting electricity demand, it might be the outdoor temperature, right, which would influence heating and cooling demand. It could be the hour of day, the weekday, the season, stuff like that. And then the x variables here, the xi, these are our decision variables, are parameters in our model. So they're basically weights on each of the features. And we want to choose the decision variables x such that this mixture of all the AIs and the XIs, this thing is approximately equal to BI for all I. So if you find these numbers, 2.7 and 0.003 or something like that, if you multiply them by the values of, the outdoor temperature, sunshine, humidity, stuff like that, that you get something that is very close in all of the examples that were given to the target B. And so we quantify closeness of satisfying this equation here. We quantify that by basically taking, the B over to the left-hand side. So subtracting that, then we'd have something that should be close to 0. And we want to minimize that. Basically, x squared is equal to 0. If your x is, x squared gets bigger and bigger as you get further and further away from 0. So we're penalizing deviations basically from the left-hand, between the left-hand side and the right-hand side here. Okay, so that's least squares, and this is one application of least squares. And not to give away the game, but in machine learning, really, there's kind of a different objective, which is we don't necessarily just want to make these things match in what's called the training data set, the data that you're given in order to do this optimization, but also in unseen data, validation or testing data. So you don't just want to do well here, you also want to do well in unseen data that comes at you in the future. Okay, so we'll talk more about how to do that later. So that's one problem class that is convex and very useful, kind of ubiquitous in applied math, is least squares. Another one is what's called linear programming. And here, basically, everything is linear. So the objective function is linear. And then we have a bunch of linear inequality constraints, which we write as a matrix A times X less than or equal to B. And here, this goofy, squiggly less than or equal to sign is just denoting component-wise or element-wise inequality. So if you have two vectors, X and Z, y less than z just means that each component, is less than each component of z. And so there's no analytical solution for linear programming. It's kind of weird. Like you'd think that this is like really simple to write down. Everything's linear, nice and clean. But actually you can't write down an analytical solution for a general linear program. But there are lots of good algorithms. A classic one is called the simplex algorithm that was developed in kind of the 50s and 60s. But there are other algorithms that work well for linear programming. And the solve time, kind of in the worst case, is again proportional to n squared times m, which is really the same scaling that we saw in the least squares problem. So again, linear programming is, it's in P, right? It's a polynomial time thing, and it's among the easiest problems that we can solve in optimization. And there are lots of tricks that you can use to transform nonlinear problems into linear problems. And it used to be like from 1950s through like the 80s, kind of the only kinds of problems that we could solve exactly and efficiently were linear programs. And we didn't really expand that. Quadratic programs maybe to some degree as well. But so there became this whole science basically of trying to put things into the linear programming form so we could use this well-developed computational machinery to solve them. Okay, so an example of linear programming that's kind of similar to the example I showed for least squares is what's called Chebyshev approximation. I'm totally mispronouncing this. Russian genius mathematician named Chebyshev. I don't know. Does anybody speak Russian? No. Okay. Anyway, so the basic idea here in Chebyshev approximation is that we have the same interpretations of x, a, and b as we had in least squares. So x is our parameter vector. A is our feature matrix, again, our matrix of like things that are going to be useful for making predictions. And then B is our target vector, the stuff we're trying to predict. And again, we want to choose X such that this mixture of the AIs, or the columns of A, is approximately equal to element B for each of the elements in our equations here. And instead of using the least squares objective, which is this quadratic thing, we use the maximum absolute error. So again, we have a thing that is equal to 0 if our equation holds exactly. But if it doesn't hold, then whether we're overshooting or undershooting, we still get a penalty. So Okay, so this thing is not a linear program, but we can do some modeling gymnastics to transform it into a linear program. I'll show a couple slides of how to do that. Okay, so here we want to choose x, again, to minimize this maximum over all the I of this absolute value fit. So we can broaden that a little bit by introducing a new variable y. And now we want to choose both x and this variable y. So our decision variable is now an rn+1, subject to this absolute value thing, less than or equal to y for each of the I. So for each example in our training data set. So you can see how these two are kind of equivalent, right? You want to make y small, basically. So you're going to push it down until it hits sort of the largest of these absolute value terms. And so this is not yet a linear program, but it is getting pretty close. So one more step basically can convert this thing here into a linear optimization problem. And the reason this is nonlinear is because we have the absolute value things wrapping this linear function. So an absolute value has a kink in it. It's not a linear thing. But we can write an absolute value in terms of sort of linear programming stuff, a linear objective and some linear constraints. So suppose we have some variables u and v, and we want to satisfy some constraint that says the absolute value of u is less than or equal to v. So here is our absolute value of u function. This is 0, and then here is v, and we draw a line up there, basically. So that is equivalent to making sure that this line here, the line u, is below v, and making sure that this line over here is below v. So now we can take the absolute value constraints that showed up in the Chebyshev approximation problem, and we can write them in this way, with a negative u and a u, both less than or equal to the same thing, v. So the right-hand side that showed up here was y. That doesn't change. And the left-hand side, we just take this thing and its negative and constrain them both to be less than or equal to y. So now we have a linear objective. It just picks out one component, the n+1 component of our decision variable. And we have a couple, actually a bunch, 2m linear constraints. So this is now a linear program, and you can apply all kind of the very robust and highly developed linear programming machinery to solve this thing. So just as a quick example of what that looks like for least squares or Chebyshev approximation. So here's kind of a dummy problem that I just made up. We have some data that comes from some unknown function. So again, the b's, these are the things we're trying to predict, and the z's here will be our features. And they come from some unknown function f, which is just a function I made up, basically, but I didn't feed that function form to the optimization, so it doesn't know. And then we want to approximate b, basically, we want to approximate this function f by a cubic. So we want that form to be basically x plus x2z plus x3 z squared and x4 z cubed. So now we have 4 decision variables, x1 through x4. So that's the dimension of our problem. And the matrix that we're using here, our feature matrix, basically is just made up of all of the polynomial terms that show up in here. So we have a 1 term, a z to the 0 term, z to the 1, z to the 2, and z to the 3 terms here. So I'll just compare how least squares fit looks and how the Chebyshev approximation fit looks. So over here, I'm showing a bunch of data. You can see this thing has kind of a vaguely, looks kind of cubic, right? For some coefficients, maybe a negative sign in there. And we're trying to basically come up with a function that gets close to all of these scatter points here. So that's all our BIs, basically. And the blue is the fit that comes out of the least squares algorithm. And then the red is the fit that comes out of the Chebyshev approximation. So you can see that the blue is kind of sitting in the middle of the data, right? But the red fit, it's trying really hard, actually, to get up here with all these outliers. And I put intentionally outliers into this problem to make the difference more apparent between the Chebyshev and the least squares approach. So basically, that leads to errors. So here I'm showing a histogram, which basically just takes the range of the differences between the data and the fits here. It takes those and it divides that space up into a bunch of bins. And then the y-axis here is just how many times did we land in one of those bins. So if you've taken a probability in a stats class, this is basically the distribution, the empirical distribution, or the histogram. So for the least squares fit, we're sitting kind of nicely in the middle here. We get this sort of bell curved or Gaussian looking thing. But you can see that we have a bunch of bad, I guess, under predictions here, where our error is like -2. And so the Chebyshev fit says, I don't care so much about what's happening in the middle. What I really care about is knocking down these outliers, predicting those better. And so you can see that the what's called the support of the distribution, basically just the extent that is covered by the distribution here, is smaller on the low end for the Chebyshev approximation than it is for the least squares approximation. So here we're missing, worst case by 2.5 or something, and here we're only missing in the worst case by about 1.5. The price we pay for that is that we take the distribution and we move it way over. So if we looked at the median or the mean of this distribution, it'd be like 1. So that means on average, we're missing by 1. We're like over predicting by 1. But the worst case is better. So this gets to like, what is your objective when you're trying to do a fit or come up with a problem? Like, do you want to do well on average, or do you want to do well even in the worst case scenario? Or is it something in between? Yes, go ahead.
So basically, you cannot say which one surpasses the other one. So it depends on the problem.
Yeah, so the question is, we can't really say definitively in this example which of these is better, right? It sort of depends on the application and stuff. I think that's right, yeah. So, I mean, so here, Chebyshev is the best when we define, a goodness metric in terms of the absolute value of the errors. But the least squares approximation is best when we define goodness in terms of a quadratic penalty on these errors. So, you can stare at this as the modeler and you can say which of these fits is better for me, right? And probably most people would say, well, the blue one, it's kind of in the middle. It looks better, right? But if you're in some situation where, you don't really care about average performance, you care about, some safety critical thing. So like if you miss this by 2 rather than 1.5, like an astronaut dies or something, right? So in that case, you might say, look, if I use a little more fuel because I'm inaccurate on average, that's fine. What I really want to do is keep my people safe. So in that case, you might say, like, I want to take a very conservative approach, right? And so there, maybe the Chebyshev approach is actually better. So this is kind of the subtlety of optimization, is oftentimes it's not really mathematical. It's not really computational. It's more about just understanding and clearly stating what it is that you want in a problem. And so very often the workflow of optimization looks like specify a problem, find a solver for it, get a solution, and then be like, well, that looks terrible, even if it's the best possible solution for the way that you specify the problem. And then you go back and you re-specify. You say, oh, it turns out actually there was something I didn't capture in the formulation that I really care about, right? Safety or energy or whatever it is. And then you go back, you tune up the formulation, you solve again, and you iterate. That's a great question, though. Thank you. Okay, so more generally than least squares or linear programming is this set of problems called convex optimization problems. And they look just like basically the general problem that I wrote down looked. We're choosing some vector and Rn. We want to minimize some scalar valued function, and we have m inequality constraints, all with 0 right-hand sides. But we add this additional specification, which is that all of these functions have to be convex. And again, I've said that word like 1,000 times this lecture, and you guys are still scratching your heads. It's a notion of curvature, right? So it just means in a scalar case, you're looking at something that's kind of bowl-shaped rather than squiggly or like an upside-down bowl. But it has a generalization to n dimensions, and we'll talk about that next lecture. So for convex optimization problems, there is no analytical solution, right? Similar to linear programming in general, but there are good algorithms similar to linear programming. And the solve time is about proportional to the bigger of either n cubed, where again, n is the dimension of the decision variable, or n squared m, which is the same thing that showed up in both least squares and linear programming. And so convex optimization includes the least squares problem as a special case. Turns out that that problem is convex. And it includes linear programming as a special case. Turns out that linear functions are convex. And so the only things that showed up in linear programming were linear functions, and so that qualifies. But also a lot more. Quadratic programming, where we have quadratic objectives, a class of problems called semi-definite programs, where you have basically a matrix valued variable, which has to be It's called positive semi-definite, sort of a generalization of positivity that goes to matrix things. Something called second order cone programming and other kinds of cone programming. So we'll talk a little bit about these other problem classes, but the cool thing about convex optimization is you don't have to know too much about what's going on under the hood. You just basically have to be able to certify that your problem is convex. Then you pass it to a convex solver. It passes you back an answer, and you kind of, walk away with a certificate that you did as well as it is possible to do for your problem. So here's the workflow, I guess, that I just mentioned in your question, Naresh. But basically, the idea here is you first formulate your problem. So you think, what do I really care about? What's an objective? What is a hard constraint that I just absolutely won't compromise on, right? Something that if it's violated, it's like just a total failure. My robot fell over or fell into a pit of lava or something like that, right? And then you hopefully, if all goes well, you recognize that your problem is convex. But more often what happens is you recognize that something is non-convex in your problem. And then either you do the modeling gymnastics that we talked about today to reformulate your problem as convex, or you come up with an approximation. So you say, oh, this thing here, I'm going to linearize, and that thing over there, I'll model as quadratic, and so forth. And then you take your thing, either your approximation or your true formulation, and you code it in a convex modeling language. And there are a bunch of these. CVX is a MATLAB toolbox. CVXPy is a Python tool. Convex.jl is in the language Julia. CVXR is in the stats language R. And there are other tools that can do stuff like this. And then basically you tell the modeling language to solve. You say, go, run, bring me the solution. And like a faithful dog, it runs off and it talks to a solver. And again, there are many, many of these. Some are free and open source, developed by mostly academics. Some are commercial products that you buy, although students usually get free access. So something to bear in mind. But basically, these things will take a problem specification and a very precise, rigid specification, and then they will run an algorithm on it and return the result. And so what these modeling languages basically do is they take your kind of human language specification or mathematical specification, pen and paper kind of spec, and then they do the complex modeling gymnastics that are needed to put it in the very sort of rigid and precise form that the solver needs. Okay, and then you get back a solution, and you kind of think, is this really doing what I wanted it to do? Could maybe I reformulate my problem a little bit to emphasize something different? So you tune the formulation, and then you run it again, and you basically iterate until you're like, yeah, this is good. The performance is good, and then you go. Maybe you go to hardware, or maybe you go to the next level of testing or something. Okay, so where are we going from here? So again, today this was kind of just a broad overview of optimization. We talked a little bit about tractable and intractable problems for a certain notion of tractability. And then we talked a little bit about basically convexity and a couple of special cases of convex optimization problems, and how they can be useful for stuff like data fitting and machine learning. So next lecture, we'll talk about convex sets and functions. So again, we said this word a million times. We'll figure out what it means in the context of either a set or a function. Then we'll talk about how to solve convex optimization problems. So I'll introduce you to CVX, the MATLAB tool. But we'll also talk a little bit about the algorithms that run in the solvers kind of behind the scenes. Again, you don't need to know that stuff, but I think it's kind of cool. And also it's kind of nice when you're using a tool or a machine to kind of know a little bit about what's happening under the hood. And then we'll do maybe multiple lectures on optimization examples that come up in real DER applications. Okay, so any questions about today's lecture? Who's been a TA so far in grad school? Do you guys, do you grade only, or do you do like a recitation or discussion section? Office hours? Yeah. It's so funny, I don't know, like we all did recitations, we all taught when I was in grad school, but I guess we don't do that as much here. Anyway, a trick that I learned was when you ask a question, you're like, so who thinks X or who thinks Y? But you have to just wait. So oftentimes like people feel awkward and then whatever. But if you just wait and wait, like sometimes people feel so awkward that they're like, I gotta speak up, and then their question comes out. So the trick is to sing the Jeopardy theme song in your head after asking a question. So you can just imagine whenever I ask a question, that's what I'm doing. But anyway, that's cool. No, this is it's a little further afield from the engineering applications that we've been talking about. So it makes sense that you guys maybe don't have questions today, but that's okay. So I think what I would like to do in the remaining 10 minutes here is basically just to look at the code that's in this week's homework. And maybe I'm doing this a little bit late. Maybe you guys have already done the homework. Mostly, I think it's due tonight. Is that right? Yeah. But anyway, there was a comment that came up a couple of times in the mid-semester feedback that you guys wanted to see more about like what was happening with the code. So it wasn't just a black box for you guys. So I would like to go through a couple of the functions that are used in this week's homework. So again, these things are up on GitHub, but I'll show you what they look like on my computer. And actually, I want to begin. I don't know if people know this, but in MATLAB, every time it boots up, it looks for a function in your MATLAB home directory, sorry, a script called startup.m. And this doesn't exist, this file by default, but you can write it. So who's done this before? One person. Okay, so this is basically a way to set up preferences in MATLAB that are non-standard. So if you want the bell to turn off, for example, you don't like it when it goes bonk bonk whenever you make an error, you can do that. So there are some standard things that I think MATLAB should do. So what I do basically, I have a subroutines folder of things like unit conversions and stuff like that I use regularly. And so I add that stuff to the MATLAB path so that I can just call those things no matter where I am in a script or a function. I also, I don't know, I have particular preferences for charts and figures and graphs and stuff like that. So I changed some graphics settings. You may have noticed that in the code that I give you guys on GitHub, it always starts with like a bunch of scrambled up lines of code around the figures. But what I'm doing here is basically setting LaTeX as the text interpreter so that I can use basically nice mathematical symbols and the legend labels and things like that. Changing the font size because I have old eyes. I do that for things like the axes and the legend and things like that. And then also I make the lines a little thicker. So by default in MATLAB, the lines are just really thin for my taste. So I change those. And I turn the beep off, and I don't like it when it gives me 16 digits of accuracy for answers. I'm like, just tell me 4, that's fine. So I do that as well. And I used to have other things in here over the years, but I kind of slimmed it down from there. The risk of a really highly customized startup.m file is that you can end up with like a bunch of dependencies that don't show up in your code, right? So that's why like I have to put these things in all the scripts that I share with you guys. So it makes the code a little bit less shareable potentially, but more convenient to work with. Okay, so anyway, I have that stuff in the startup.m file. Then I have this simulate water heater file here. And so what this does, basically taking it from the top, is it specifies the parameters that we talked about for our water heater model. And I forget which model I'm using here. It might be either the lumped sensible model or the stratified sensible model. So anyway, I start by talking about the tank volume. So if you talk with like normal people and you ask them, how big a water heater do you have? They'll say, I don't know. But if they do happen to know, they'll say, oh, I have 50 gallons or I have 80 gallons or something like that. So typically it's a volume measure. And then U here, this is the thermal transmittance of the insulation in the tank wall. So, the resistance is equal to 1 over UA. So I take basically those two parameters and I say, okay, give me back a water heater that matches those things. And then the parameters that it gives me back is the thermal resistance between the water and the surrounding air, and then the capacitance of the tank. And so this function here, the subroutine get water heater parameters, it basically just says, okay, I'm going to assume a tank height of 1.5 meters, 4.5 feet, something like that. And then set the radius of the tank, basically using equations for cylinders, or I guess, yeah. And then set the surface area of the tank as well. And so this has both the tank walls and also the top and bottom surface area. And then based on some equations that I showed in lecture a couple of weeks ago, it sets the R and the C value from there. So see this 1.2 that shows up in the C, this basically comes from the thermal capacitance. No, sorry, this comes from the density and the specific heat capacity of water, basically. Okay, so now we have the RC parameters for a water heater. So I define the time span. Here I'm saying let's find the start time as 0. So that'll be like midnight. And then the final time is a day. So if you wanted to simulate for 5 days rather than 1 day, you could, put a 5 up here. I set the time step dt, and here that is in units of hours. And then I've taken 5 divided by 60, so that's 5 minutes basically. And then t, the full time span. So this declares a vector that starts with the first element at t naught and ends with the final element at tf. And then every element in between is separated by a difference dt. And then k shows up in some of the code. So I just define that. That's the number of time steps, which is the length of the time span minus 1. Okay. So now down here, I'm defining the number of occupants in a house. And then I have this other function, generate water draws, which randomly generates some plausible water draw behavior for a home with n occupants. And I give it the time span, so that it knows basically if it wants to put showers in the morning or in the evening and how to do that. So what that function looks like, I just pass in t and n, but I'm gonna need k, the dimension there. So I get it by just looking at the length of the time vector and taking 1 off of that. And then dt again comes from just the difference between t1 and t2. Okay, so now what is this doing here? So I initialize qd, that's the thermal power associated with the water withdrawals from the tank. So I initialize that at 0. And then I'm going to do n water draws, basically 1 bath or shower for each occupant in the house. And you may remember from the water heater lecture that basically most of the water usage in a home comes from showers and baths. There's some other stuff for dishwashing and hand washing and so forth, but those tend to be small effects compared to showers and baths. So I initialize some indicator that says, is this a valid water draw or not, basically? And that's going to have to do with, does it fall in kind of reasonable times for a shower? So I start at 0, and then I just loop until basically the thing becomes valid. So I'm generating a bunch of random things, throwing away the ones that don't work and keeping the ones that do, essentially. Okay. So I start with k rand I. This generates a random integer between 1 and the argument k. So if k is like 24, if I was using hourly time steps, then I would be running basically from between 1 and 24 randomly. And then this scrambled up looking piece of code here, all this really says is the hour, or it associated with the water draw, is it between 5 a.m. and 9 a.m.? So is it a morning water draw? Or is it between 20 and 22? So I guess that's 8 and 10 p.m. So an evening water draw. So if it is, I say, okay, that's valid, I'll keep it. If it's not, I throw it away and try again. And then we want to generate basically the duration of the shower. So I do that. Let's see. So I take the sort of random duration in minutes, somewhere between 7 and 13 minutes, which I kind of just made up. The idea being a 10-minute shower is sort of normal, but some people will go fast, some people will go slow. And divide it by 60 to get hours. And then the power draw during the shower. So this has to do with basically how hot or cold the water is that people like when they're showering. So if I draw a little bit, or if I want a colder shower, I'll draw somewhat less hot water and mix in more cold water. But if I like a really burning hot shower, then I'll draw more power, essentially. So here's the power. And then the energy that's drawn, the total amount of energy that's drawn from the tank is just the product of the power and the time. So then basically what this step does is it just takes the amount of energy from the water draw and it spreads it out over the time steps. Because dt, the time step is 5 minutes in this example, but it could be 1 minute or 1 second. And so rather than putting all of the energy in the time step, which could lead to very, very high spike in power if our time step was really short, I just take it and spread it out over an appropriate number of time steps. So that's what this code essentially is trying to do. And then we generate a bunch of parameters. I think I'm running low on time here, so let me run this and just show some of the output. So yeah, what's the minimum amount of water in the tank? Call that 0, the maximum. Okay, and I define the hot layer and the cold layer temperature. So I guess I'm using the stratified model here. So T hot is 52 Celsius, which is, I don't know, 150 or something like that Fahrenheit, which is a little hot for a water tank, but not too bad. And then 15C is about, let's see, about 60, 55 Fahrenheit, somewhere in there. So that might be roughly the temperature coming off the water mains under the street. And then W, this is basically a disturbance term that has the water draw primarily in it, but it also has some term related to the leakage through the tank. So this is just the model that showed up in the lecture slides. And then I run the water heater control function. And I do it in a number of cases. So there's a resistance only, a heat pump only, and then a combined or a hybrid simulation. And so the code of this, I guess I won't show you because it's your homework. But let's see what happens if you run it. I changed the time to 5 days rather than 1 day. So let's see what happens when you run it for 5 days. Oh, I see. So I had rearranged some of this code and not defined beta, I guess. All right, so I think, yeah, my code is a little weird, so I need to fix it. Basically, I designed the code for a 1 day time span, and so really I should have something rather than if t is between 5 hours and 9 hours, I should have like if mod t 24, right, is between that time span, then this would work. So I guess we can see if I can do that real quick, but we're also over time, so I'm going to do that and do the live coding if you want to watch. But if that is super boring to you, please feel free to leave. Okay, so to tune this up here, this is the line that needs to be fixed, right? So what I'm going to do is rather than taking t, I'm going to take mod of t, comma 24. So if t is equal to 25, that's going to return 1. Basically, mod is the result of the remainder after integer division. So if I do that, and I do this, and then one more over here, I think it should work. Okay, so now we've got more water draws. Sort of seems like not quite enough, but anyway, so you can see the basic behavior when we're doing resistance only. We use the whole 4.5 kilowatts of resistance to recharge the tank. When we do heat pump only, we only ever use the heat pump capacity, about 500 watts in this example. And then when we're doing combined, a hybrid unit that has a heat pump and a resistor, whenever we drop below this threshold, we use the resistance backup. So about 5 kW because we're using the resistor, 4.5, and the heat pump at half a kW. Okay, so that's all for today. Sorry for keeping you a little bit late, but I wanted to walk through the code a little bit since you guys asked for that. So have a good weekend, and I'll see you on Monday, Tuesday.